Today you're going to learn about complex numbers, and the reason we need complex numbers is mostly electrical engineers needed them. It is not a real number, but it is a complex number. So let me explain it just a little bit further. A complex number is when we have to square root a negative number. And so electrical engineers created a complex number. For example, x squared equals -1. If you would square root both sides of that, you would say there are no real solutions, which is still true. But since engineers needed to use negative numbers and needed to have a square root of them, they created an imaginary unit called I. So I is equivalent to the square root of a -1, which then means if I would square both sides of this, I would get I squared equals -1. And whenever we have to square root a negative number, it will be I as its square root. A couple properties to know about imaginary numbers is that if I take the square root of a -r, it would equal I times the square root of r. The reason that works is because this is like the square root of a -1 times r, and the square root up here of a -1 is I. So this part would come outside as an I, and I'd have I square roots of r. An example here is the square root of -5. Well, the square root of -5 is -1 times 5. So the square root of a -1 is I. So I have I square roots of 5. Also to note that when you have I square roots of r quantity squared, what that means is I square roots of r times I square roots of r. I times I is I squared. Square root r times square root r is r. All I squareds are replaced with a -1. So this becomes -1 times r, which is -r. An example of that would be I square roots of 5. That is I squared. I square roots of 5 times I square roots of 5 is I squared times 5. I squareds are replaced with a -1, so it becomes a -5. Now, as I said before, electrical engineers always use square roots of I, or square roots of -1, which is I. But can you think of any situations, since complex numbers are never real, they are imaginary, that means they will never touch the ground or the x-axis. So can you think of any situations that are parabolic but never touch the ground? I'd like to share one with you, and it is bungee jumping. There is no sound to this, but please watch, and we will be very thankful that bungee jumpers never touch the ground. All right, they're getting ready to jump. There they go. Boom, back up. Thank God they didn't touch the ground. That is a beautiful example of parabolas that never touch the ground, where I would use an imaginary number. And if you would refer to your worksheet 5.1, exercise number 2 never touched the ground. It was a graph that was down here. So that never touches the ground. It comes up and comes back down, but it never touches this x-axis. And I believe that exercise number 5, no, not number 5, let's see. Number 3 also never touched the ground. No, that one did. Exercise 3 also never touched the ground. I believe it looked like this. So notice it never touches this x-axis either. When we have complex numbers, they are broken into several categories. We have complex numbers. The real numbers are a subset of complex numbers, because they would be A, the real part, plus no imaginary part. Two kinds of real numbers, as you recall, are either rational, those that can be written as fractions, or irrational, like pi and square root 2, that cannot be written as fractions. Another subset of complex numbers are the imaginary numbers, where we have a real part, plus bi, an imaginary part. Would be like 2 plus 3i, or 5 minus 5i. Those are imaginary numbers. Or we could have pure imaginary numbers, which is no real, just imaginary, negative 4i, 6i. So the set of complex numbers is made up of reals, imaginaries, and pure imaginaries. Let's start to do some exercises where we actually use imaginary numbers. So if we solve this first equation, 2x squared plus 26 equals negative 10. We would subtract 26. 2x squared equals negative 36. Divide by 2. And x squared equals negative 18. Now to undo a square, I would square root both sides. And I would get x equals plus or minus. Now let's factor this. It's a negative 1 times 9 times 2. Well, the square root of a negative 1 would be I. The square root of 9 would be 3. And then I have a square root 2. So that means plus or minus 3i square roots of 2. That is a pure imaginary number because there is no real to it. And since I had a power of 2, I should have 2 roots. And my 2 roots are x equals 3i square roots of 2 or x equals negative 3i square roots of 2. Let's try this next one. Negative 1/2 times the quantity x plus 1 squared equals 5. To solve this, first you would multiply both sides by a negative 2. That would make x plus 1 quantity squared equals negative 10. I now have a perfect square on this side. So I would square root both sides, and I would have x plus 1 equals plus or minus. And again, let's factor this negative 10. It is a negative 1 times 5 times 2. Well, the only thing that factors out of there is our I. 5 is not a perfect square, and neither is 2, so it'd be square roots of 10. this is what x plus 1 is equivalent to, but I want what x is equivalent to. So I must subtract 1. So that gives me x equals negative 1 plus or minus I square roots of 10. Again, I started with a square, so I must have two roots. And my roots would be x equals negative 1 plus I square roots of 10. And my other root, or 0, is x equals negative 1 minus I square roots of 10. If we can graph real numbers, then we can graph imaginary numbers. The only thing is that an imaginary number, a complex imaginary number, cannot be graphed on a coordinate plane. It must be graphed on a complex plane. So to be a complex number, it was either a real number or it had an imaginary part to it. So our x-axis becomes our real number axis, and our imaginary axis becomes our y-axis. So if I were to plot this point A, negative 4 minus I, it is negative 4 on the real and negative 1I on the imaginary. And these two would cross over each other right here. So this would be point A, negative 4 minus I. If I were to graph point B, which is 5, only a real number, 5 on the real, 0 imaginary, would be right here. That would be point B. And lastly, if I were to plot point C, 1 real plus 3 imaginary. 1 real and 3 imaginary would be right here. So you can see it is easy to graph complex numbers when you do it on a complex plane. Now let's work with some more complex numbers, and let's take one at a time. First, it says we are adding these two complex numbers. Please listen to me and do not look at what your book does, because your book is confusing. If I'm going to add two complex numbers, I'm going to line up the like terms. So negative 1 is real, so I'm going to line up the 3 under the negative 1. And the plus 3i is imaginary, so I'm going to line up the positive 3i under the imaginary. And then I'm going to add these two. So a negative 1 plus 3 is 2, and a 2i plus 3i is positive 5i. And I have an answer of 2 plus 5i. The real part first, the imaginary part second. Now let's try that with a bit more complex version. This time I'm subtracting this one and adding this one. So it might first, let's take our 2i. And then let's distribute this negative through. So it would be a negative 3 minus I. And let's line that up under our 2i. The negative 3 is real, so I have 0 real here, and the negative 1i under the positive 2i. And then I am adding 2 is real, the negative 3i is imaginary. And I can just now add all of these. So it would be 0 minus 3 is negative 1, plus 2 is is positive 1. No, negative 3 plus 2 is a negative 1. Sorry. 2 minus I is I, minus negative 3 is negative 2i. Negative 1 minus 2i is what all that combines to be. Let's try multiplying. a negative I times the quantity 3 plus I. So we would take negative I times 3 is negative 3I. And negative I times I is a negative I squared. Well, negative 3I. On the previous page, we learned that all I squareds can be replaced with a negative 1. So this becomes 1 minus 1. So a negative negative is a positive. And imaginary parts come second and reals come first. So it would be a positive 1 minus 3I. Be your final answer. Now let's take a binomial complex times a complex binomial. So again, we would FOIL. First we would do 2 times a negative 6 would be negative 12. And then 2 times a negative 2I would be negative 4I. And then we will do 3 times a negative 6I is negative 18I. So I'm going to line it up under the imaginary. And positive 3 times a negative 2I is a negative 6I squared. So I'm going to line that up back here since it is not real. So I have negative 12 minus 22I minus 6I squared is replaced with a negative 1. So it is times negative 1. Well, that's a negative 12 minus 22I. Negative 6 times negative 1 is positive 6. Negative 12 plus 6 is 18 minus 22I. Oh no, negative 12 plus 6 is negative 6 plus minus 22I. My fault. All right. Now, if we take 1 plus 2I times 1 minus 2I, again, 1 times 1 would be 1. 1 times negative 2I would be negative 2I. 2I times 1 is a positive 2I. 2I times negative 2I is negative 4I squared. So I have 1. Negative 2I plus 2I is 0. Negative 4I, this gets replaced with a negative 1. Negative 4 times negative 1 is 1 plus 4 is 5. Notice how by multiplying 1 plus 2I by 1 minus 2I, I got a real number back. These two are very special because they are called conjugates of each other. A conjugate is the factor of the difference of two squares. So what does that mean? If you look at the first term, 1 and this first term is the same. You look at the last term, 2I and 2I. It's the same. One is plussed and one is minused. So the first and last terms are the same. One time you plus, one time you minus. So if I say 3 minus 2I, what would its conjugate be? 3 plus 2I. How about if I say negative 4 plus I? What would its conjugate be? Negative 4 minus I. Now the reason you're going to need that is because we need to simplify some I expressions. Conjugates are needed to simplify imaginary numbers. And since you can never have an imaginary in the denominator, that is when you're going to need to multiply by the conjugates. For example, 3 plus 11I over negative 1 minus 2I. Since you cannot have square roots in the denominator, and I is the square root of negative 1, we cannot have an I in the denominator. So this acts as one term. So if I multiply by its conjugate, I should get a real number back. So the conjugate to negative 1 minus 2i is negative 1 plus 2i. What I do to the denominator, I must also do to the numerator. So I must also multiply the numerator by negative 1 plus 2i. So let's do that first. 3 times a negative 1 is a negative 3. 3 times a 2i is a positive 6i. And then I have 11 times a negative 1 is a negative 11i. And a positive 11 plus 2i is a positive 22i squared. All right. So that gives me negative 3 minus 5i. This gets replaced with a negative 1 minus 22, which gives me negative 3 minus 22 is a negative 25 minus 5i for my numerator. Now let's do our denominator. Negative 1 times negative 1 is positive 1. Negative 1 times 2i is negative 2i. Negative 2i times negative 1 is positive 2i. Negative 2i times a positive 2i is a negative 4i squared, which gives me 1, 0. All i's are replaced with a negative 1, so I have plus 4, which is 5. Is this in simplest terms? No, it is not, because 5 goes into both negative 25 and into negative 5. In order to simplify, the denominator must divide into both terms of the numerator. So since 5 divides into negative 25 and into negative 5, it simplifies to negative 5 minus I. And one last thing is finding the absolute value of a complex number. The absolute value of a complex number means we're going to find the distance of a number is from 0, 0 of the origin. So if we're finding the distance, the way you do it is you would take the real part, a squared, plus just the coefficient of the imaginary part, b squared, and square root it. So let's try this one. The absolute value of a negative 2 plus 5i will equal the square root of the real part is a negative 2. So it would be a negative 2 squared plus the imaginary coefficient, which is positive 5. So it would be 5 squared, which is negative 2 squared is 4, plus 5 squared is 25, which is the square root of 29. So negative 2 plus 5i is square root of 29 units from 0, 0. In other words, on a coordinate plane, negative 2 plus 5i is right here. To this point creates this distance of square root 29. Let's try this one. The absolute value of 5 minus 3i. So it would be the square root of a is 5 squared plus b is negative 3. So negative 3 squared, which is 25 plus 9, which is 34 square root. Go ahead and try this assignment for tomorrow, and I'll be back to answer any questions you have on it.